Welcome everyone. This is the second part of my freezing test series, and in this video I'm going to test the TEC12706. So this is the 6 ampere unit. In my previous video series I was testing these coolers without any kind of heat load, so the cold side of these units were covered and surrounded, so there were no or very little negligible heat transfer between the cold side and the environment basically, but there was no objects attached to it. So I measured the currents and the different temperatures, and I concluded some results. And here what I do is I see what is their performance when you attach some known load. And this known load here inside this chamber is the aluminum tank, which is 87 grams. This will be important for our calculations. And the tank contains about 100 grams of water at roughly 23 degrees Celsius. So that will be our heat load. And we will see how long it takes to cool it down to 0 degrees, and also to basically finish the freezing process of the water and then further cool it down below 0 degrees. Because you know that first you have to supercool the water, so we slightly shoot under 0 degrees, and then the freezing process starts, so the temperature goes back to 0 degrees, and as long as the freezing process hasn't finished, the temperature stays 0 degrees, and after the whole volume of water is transformed from liquid to solid, then the temperature of the ice block will start to decrease again. And this is related to the latent heat of the water. So as long as we are freezing the water, so we basically support the transformation between liquid and solid phases, we are fighting against the latent heat. And after the liquid phase disappeared, we don't have to fight against it anymore, and we can cool the now ice material. So that's what we will do here. And from the TEC12706 test, we concluded that we are around minus 22 degrees, if I remember correctly, and 4.8 amperes when we are like at the minimum of the current versus cold side temperature curve. So what I will do, in order to make my job a bit easier, I will apply 5 amperes, because then I can read the performance chart of this device easier. So I will say that I will apply 5 amperes, and then we know that the delta T should be 23 roughly, and then I will see what is the cooling performance at that given setting. So of course the cooling performance won't be precise, because first we start at this point, but as we start to decrease the temperature of the system, that changes, and the current is changing slightly. So this is just an estimation, so don't expect me to demonstrate some Nobel Prize worthy experiment here, but at least these are some demonstrations that you can do some valuable measurements at home as well. So we will obtain the QC from the performance chart. I expect it to be around 25-30 watts, but I will do the calculations and I will show you how to evaluate the performance charts, so don't worry, but that comes after I finish the measurement. So 6 ampere unit will be running at 5 amperes, and we will just monitor all the temperatures. And there are now some improvements. First of all, I have this new connection. So I have this screw type banana plugs, and the fun fact is that I can also screw this part of the banana plug, not only this part. So this is very cool, because I can like precisely adjust the height of the cable and also the tight the tightness of the cable. So this is very cool. But what I did here, I had some leftover cables from my speaker cables, and I used those here. And the reason behind that is because previously I was using 2.5 square millimeter cross-section area cables, and even those cables were becoming hot when I was around 10-15 amperes. And my power supply, which is connected with this cable, is capable of producing 20 amperes and 30 volts. So then I thought that, okay, I will go to higher currents with the higher units, and I don't want to have any kind of fire danger and stuff. And also this looks quite cool, so I thought I should assemble this kind of connection. And also it's much more easier to work with these banana plugs, because now I can use another banana plug like this, and this can be connected to my multimeter, so I can measure the voltage here easily, and that's very good. So this is one of the improvements. And also there is a zip lock here, so the cable won't spread all along its way, and then I can easily attach the current meter. So this is also something good. And I have a previous video where I made this thermometer, 4 channels, and it contains 4 LM335 modules or thermometers. And what's special about this is that it can save the data on an SD card, and I can start and stop the acquisition, and it saves the data and also the time of the measurement. Not it's only the elapsed time, not the real time, but it saves it to the SD card. So for me it will be much easier to work with the data. And also now we have 4 thermometers connected to the very same device, and I save up some space as well, and it's a bit less hassle to just work with this single unit. And I strongly recommend you to check this video. It's a bit lengthy, almost 1 hour, but I explain everything, why I do this, why I need it, how I built it, and how the code works behind this. So everything is explained. It should be clean, it should be clear, and then you can see that we have the numbers and everything. And you can see we have 4 thermometers attached. They are roughly at the same temperature. The number 2 is a bit outlier. I strongly believe that the reason is because the value of the resistor for this particular device is a bit different than the others. All of them should be like 2 kilo ohms or 2.2 kilo ohms, somewhere around that. But I remember that this was a bit outlier. So maybe I will change it in the future just to have more comparable. But what I could see is I can say when I process my saved data how comfortable that I have the data, right? So I say that, okay, I take the average of the other 3, and then I subtract the 3 from that. And then we always just need some relative changes, and that's all. So this will be fine. But what I want to say here, that the number 1 is connected to the outlet, so that's the hot or warm air which is coming out from the CPU cooler, which is attached to the hot side of this device, the TEC12706. And then we have number 2. Number 2 is in this corner, slightly in the water, so it's more or less in the top layer of the water. And then channel 3 and channel 4 is in this corner, but channel 3 is almost at the bottom of the tank, and the channel 4 is more or less in the top of the water. And it was a bit difficult to place these cables because they are quite rigid, because this is a shielded cable, so a lot of layers are inside that cable and a lot of wires. So enough talk. Let's just summarize what we have. 4 different thermometers measuring different points of the water. We will apply 5 amperes, and based on that I will evaluate the performance chart, which I will show after this. What else? basically that's all. So we will see how this freezes, and I will let this thing to freeze totally. So it should reach the ice should reach all the corners, and then it should cool down below 0 degrees, and hopefully the ice will not squeeze my thermometers. And what I will do now, I will switch the camera into time-lapse mode. So for a few minutes maybe it will be silent, but I will put some subtitles to just say what is happening, if something is happening or anything is happening, but I don't expect too much action. The water will become a bit more turbid, so that can be something interesting, but that is because the ice is started to form, or it is forming. Then let's just start the measurement, and let's see what is happening. So I conclude the experiment here, and I strongly suspect that something is wrong here, because this has been running for quite a long time, and I still can see some water inside this container. But most of the things are ice inside. I can remove this, and I can measure it. So depending on where I measure, it can be anything between 0 and -7 degrees. But at least most of it is ice. And one interesting thing that we can see, the water solidifies as we expect, or as I expected. So the container is of course a good heat or thermal conductor, which means that it will pick up the temperature of the cold side of the Peltier quicker than the water, let's say, inside the container in the middle or in the sides. I would say in the sides here and there, because those are like the further away, they are far away from the sides and the middle. So the ice starts to grow from the sides first of all, because the aluminum is colder, and then it grows in the middle as well here, because of course the Peltier is just under that area, which you can see it is a frozen area. So if I measure that, it's like pretty cold. So 5.7 minus, and then of course this is the water. Yeah, so this is cold, but the issue is that the water is still not cold enough. And then I measured the back side of the heatsink, which is now at 35 degrees Celsius, which is of course 5 degrees below the outlet temperature. So that's something to consider. And also now I start to suspect that the hot side of the Peltier can be even higher than this value, the 35 degrees. So maybe the hot side of the Peltier is maybe even 50 degrees. But then I have to consider this in my calculations. So what I will do, When I calculate now these things, I will do an idealized calculations, so I use the numbers which I assume, and then based on the evidence and the time and the measurement values that I collected, I will recalculate the things backwards. So instead of using the heat, the cooling power provided by the Peltier, and calculating the time for cooling, I will go back from the time which we were using to, let's say, reach this kind of temperature, and try to estimate the cooling power. And I think that the cooling power will be much lower than I would expect, and that's mainly due to the hotter hot side than expected. So let's just wrap up everything here. So we were running this for an hour maybe, or more, I would say even more, and the hot side is maybe hotter than we expected, and you can see that most of the things here are in ice condition instead of liquid water. But the big thing is that we cannot stir it, and that's a big problem, because the heat conduction of the water is very bad for this purpose. So as you can see, that's why we have these blind, let's call them blind spots, regarding the freezing process, that those are just liquid water. So let's finish here, and I will move the data from the SD card. Hopefully I saved everything, and after that I just analyze the data and have some discussion. So let's see what are the numbers. So let's check the numbers first from the calculation, then we can compare it with our measurements and see what we get. So first of all, let's check the performance chart, and this is for the TEC12706. I just write it down so we don't forget it. Not 1606, sorry. So this performance chart is for the TEC12706, and you can see that the different lines here are corresponding for the different current settings, and then on the x-axis we have the DT, that is the temperature difference between the hot side and the cold side, and you have to make sure that you cool your hot side properly, so you really reach these values that are stated here. And once you know that you want to reach the certain cold side temperature with a given hot side temperature, which again depends on your cooling, you can determine the cooling power based on the current. So what you do here is, I already did it, but I show it again. So you select your DT, and I selected 30 because I was maybe naive and I was optimistic. So I said that my goal temperature is 0 degrees Celsius and my hot side is around 30 degrees, which I was like estimating based on the outlet temperature of the CPU cooler, which is cooling the hot side. So I put a vertical line here, like this. And now you can see that it cuts all the curves from the 2 amperes. So the first curve here is the 2 amperes. So for example, let's do another example. If you decide to set your current to 2 amperes while hoping that you have DT equals 30 degrees, then you have something around, I don't even know, 7 watt of QC. So this is your cooling power. So what you do here is that you go along your vertical line, and when there is an intersection with this DT line and the current line, then you grab your ruler and draw a horizontal line towards the y-axis, like this. And then you see that, okay, we went up with 1 ampere again, so this is now 3 amperes, and we went towards the y-axis, and this is halfway between 13 and 26, almost. So this should be something like 18 watts, let's say, or 19 watts, something like that. And then you just continue this practice. So I was feeding 5 amperes, as we agreed on in the video. So then my expected performance is around 32 watts of cooling performance. So let's go to the side where I have the written details. So once again, dt and not delta t, this is very important. So the dt, the difference between the cold side and the hot side given in Celsius is defined, and we chose 30 here. And then qc here on the y-axis, that's the cooling power. And then we have these details. So the qc at 5 amperes and dt equals 30 degrees Celsius is 32 watts. So that's what we have. And our initial temperature was 23 degrees, and we wanted to go down to 0 degrees Celsius. So that's basically delta T, not dt, delta T equals 23 degrees Celsius. So we have this Q equals, I write it down, Cp times m times delta T, and that is written here, but I already substituted the numbers. So we have the all properties which we want to use, and I emphasized in the beginning of the video somewhere that the mass of the material that we are cooling down is an important parameter. Well, here you go. So this is the 100 grams of water, and then its Cp is 4.18 kilojoule per kilogram times Celsius degrees, and then the delta T, sorry. And if you try to simplify the units, then you know that kilogram goes out or falls out, and also you can simplify by the Celsius degrees, so you get back with the kilojoule. And here I directly written the kilojoule values converted into watt hours, because watt hours will be more useful for us. So if you want to cool down the water 100 grams 23 degrees, or basically not cool down, change the temperature, because you can go, let's say, from 50 degrees to 27 degrees. That's also 23 degrees temperature difference, and here it's only the difference that matters, as long as you stay within the temperature range where you do not have any phase transformation. That's very, very important. For metals here, it doesn't really matter, because we will never reach those temperatures where the metal goes through any kind of phase transformation, but for the water we have quite a limited range, so we have to be careful, and you will see it later why. So you can see that this is quite a large number as compared to the aluminums, so I don't go through these numbers, but for the aluminum we need 5 times less or 5 times smaller number. So that's very interesting. But if you think about it, the metals are better heat conductors, and there is a reason for that. So that's why you also can expect some different and smaller numbers. And the mass of these two objects are roughly the same. But enough talking. So what we have to do here is basically we just summarize these two. So we just add up these two numbers, and that's how we arrive to this 3.17 watt hours. So this number means that if you have this much material with these kind of heat specific heats, and you want to achieve this kind of temperature difference, then for 1 hour you want to, or you have to feed the system with this much watts. So 3 watts for an hour will change the temperature by 23 degrees of this specific system. And then we can basically convert it that we say that we have 32 watts available, so 10 times that much, and more precisely 10.1 times. And then you take this number and divide the 60 minutes with this, so you get your result in minutes. So that's what I did here, and the final result is basically 6 minutes. So in 6 minutes we should be able to reach 0 degrees with this kind of system, assuming that everything is optimal. Optimal heat transfer, optimal insulation, and we nailed the DT value. But I was also thinking to cool down this material more. I will do a very, very simplified sketch here So don't expect me to be very scientific, but here we put the time. Here we put the temperature, let's say in Celsius. So I do something like this, something like this. This should be like a flat line, but I guess you more or less understand. And then I put it roughly here. Let's imagine that these two numbers are, these two curves are overlapping. I just cannot really draw. Wait. So I can do a trick. So something like this. And this is 0 degrees. So what is happening that you cool down your water. I just write it down. And until this point, your water is liquid. And between these two things, you have liquid plus solid, and here you have solid. So what is happening? You cool down your material, which is water. This is strictly the water. So cool down the water, reach the point where you supercooled your system, and then the nucleation of the ice, which is now will be solid, starts. So here you jump back to 0 degrees. This is below 0, so let's say -1. Maybe not even -1, but just to give you some kind of impression that you have lower values than 0 degrees. Then here you jump back to 0 degrees, and here where basically the freezing really starts to go. And as long as you have liquid in your system, you stay at 0 degrees. Here also. And then here you start to cool your system, because here you strictly cool the ice. So here, let's say -5 degrees. And what is happening here is you have the so-called latent heat, which is basically, let's say, fighting against your cooling. And it's because of the heat it's because of the phase transformation. So when you have this phase transformation from liquid to solid, this heat of fusion is has to be considered. So this heat of fusion, or latent heat, which is this 334 point something kilojoule. So this much heat you need to add kilojoule per kilogram. So if you have 1 kilogram of water and you want to get it below 0 degrees, so after you reached 0 degrees and you are at the supercooled state, so here you have to have additional 334 kilojoule energy in order to overcome this, now let's call it barrier, so to fight against the latent heat. And after investing this much energy in your 1 kilogram of water, then you can further cool it down to lower degrees. But here now you are cooling the ice, which is solid. So let's jump back to our stuff. So I mentioned that I might want to freeze the water, and I might get some conclusions from that. So this is the latent heat. So as I said, 334 kilojoule per kilogram, and we have just 100 grams of water. So basically we make a division here. So 33.4 kilojoule of energy is needed to be added in order to overcome this latent heat issue. And then I convert it again to watt hours, because that's our units, the watts, that we can work with in a better way. And you can see now that we need, and listen, additional 17.4 minutes to overcome this barrier here, the liquid plus solid phase. That's almost 3 times more than the previous time, if you just consider this. I mean, this is like roughly 3 times of the energy. So, I mean, this is a bit like amazing that you can cool down the water from room temperature to 0 degrees by using 3 times smaller amount of energy than to being able to cool it down further. So this is just some amazing fact in the world of physics, basically. So in total, we need, let's say, 24 minutes, roughly. This is a rough estimation. We need 24 minutes to get basically here, to this point. And after 24 minutes, we go down basically below 0 degrees Celsius, in like really below. So let's say to -5 or something. So now this is, I hope it was clean or clear somewhat. Now let's see what is the number that I got from the measurement, and also let's just look at the curve that I was able to measure. So these are the curves, and you can see they are quite cool. At least I'm quite proud of them, because this is basically one of my previous videos result that I put together a 4-channel thermometer. Please check that video because I think it's quite instructive, and I put everything together from the very beginning where I started to solder the things together, and until the very end where I explain the whole code that I used on the Arduino line by line. But let's jump back because this is more interesting. So if you remember, in the beginning there was a small like discrepancy between the two temperatures. That was basically one of the sensor and the rest of the sensors. So this was yeah, around 21 degrees, and this was like 26 degrees Celsius, and you can see this difference here. And I don't know, that's because maybe the very different very small difference between the resistors. So these three are more or less the same resistance values, and this is a bit I think higher. I will check it. But I think this is very obvious that this is the outlet, but also the legend should, oh sorry, this is messed up. So this is wrong, but look at this please. So, and also here this is wrong, so don't consider this. But this is very obvious, this is the outlet, which was 30 degrees Celsius. And then the rest is basically the sensors, the temperature sensors immersed in different areas of that water tank. And then let's see this bump. So at roughly 13 minutes there is a bump. And what is that bump? Let's go to the right curve. So here again you see this bump, and also not only here, but here also a slight bump, and here there is also a slight bump. And these three things were at the different points, and they show the bump almost at the same time. And of course you have some slight decrease more in the temperature, but you see that the curve like really flattens out now here. And that is basically just remember my sketch. So time, temperature, and then, and this will be ugly, sorry, this. And I really think that this bump here, where you start to go from liquid to liquid plus solid, this is solid, so this bump is quite much possible that it's this bump. So we reached the 0 degrees at 14 minutes at 3 different points. And then one thing that we should see here is that we expected 24 minutes for the time to reach this point on the phase diagram, and we are here almost at 1 hour and still nothing is really happening. So that was a bit curious, and I could still see that most of the points haven't really reached 0 degrees or haven't really went below. So if you see that we have the 0 here, of course our thermometer is not very precise, but still it should be somewhat precise. And then it's very interesting to see that we don't really have that number. And it was really interesting to see that even after like 55 minutes, so here let's say, I could still see water in the system. And of course I tried to say that that's due to the lack of stirring, of course, because then you cannot really distribute the heat, so you don't have an even distribution of temperature in the system and so on. But still it's very annoying that still after roughly 1 hour the system was not frozen. And as I said here, so around 13-14 minutes we have the bump, and then I really assume that phase transformation started here. And then if we say that, okay, this is 14 minutes, and we know that this is the amount of energy per hour that we need to feed to the system to cool it down from 23 degrees to 0 degrees. And then we say that, okay, if we reached this, or if we could give this amount of energy to the system under 14 minutes, how much energy we were feeding. So what was basically the cooling power? And it came out that it was 13.6. And that's very interesting, because if you remember our previous page, in that calculation this number was more like 32 or 33. So this is like less than half of it. So that's a bit interesting. And then I was thinking that, okay, what could have happened? So first, maybe I did some mistake here. Maybe there is something wrong in the calculations. Here, I mean, anything can happen, and nothing is perfect, so maybe I did something wrong with the calculations. But I'm pretty sure that the thermometers are more or less precise, even if this bump is like different. I mean, usually when I saw that the temperature started to reach 0 degrees, I saw these small spikes, so when the temperature went up a little bit, and then I could see that the ice started to form around those chips. And actually, when the ice entirely surrounded those areas, then the temperature started to go down more below those values. So I don't know what have happened, but I have a clue, and let me show you that slide as well. So let's get back to the performance charts of these TEC12706 units, and these are at 50 degrees Celsius. So I assume that the hot side is 50 degrees Celsius, because now I try to explain what is my assumption. So here, this is the DT versus voltage chart, and this says that if you have a certain, if I understand correctly, if you have a certain current, and you can see from this perspective that you have a certain DT, then the voltage will be like this. Or if you see that the voltage is something like this, let's say we have set up 3 amperes, and then we know that the hot side temperature is 50 degrees, so 3 amperes, and hot side is 50 degrees, then we are here. Let me do this. So we are here, and that means that the voltage is 9 volts. So what I saw on the power supply, the voltage was around 13.5 volt, and I was running at 5 amperes. So I took the red curve, because we knew that, okay, we are at 5 amperes. And then I also knew that I am somewhere around here, because that's like 13.5 volts. And then I went down, and I saw that, DT is 70 degrees. So that's a bit interesting, because then here the DT says still that this is the difference between the hot side and the cold side temperature. So, I mean, now this is not a subtraction, I just put a minus sign there, but it's... So what this says, that if I am at 5 amperes and I see that the voltage is 13.5 volts, the DT is 70 degrees, and I'm pretty sure that the ice was in that box, it was almost full of ice, so there was some water, but very small amount. So this suggests me that the hot side temperature was actually hotter than I was expecting it to be. And then if I choose this dt equals 70 degrees and I still stick to the 5 amperes, so then I go to the other chart back to here. So I pick 5 amperes, red line, and I go to dt 70. I already drew it, so sorry, that's a spoiler. So I pick the 70, go up, cut the 5 amperes, go left. Oops, that's 6 watts. Half of the value that I calculated, that was 13.5 or something like that, 13.6. But this is closer to that value than the 30 something. And if I say that, okay, maybe the dt was smaller, or maybe the current was smaller, but that's not possible because I read the current. So something must have happened there. And I measured the back side of the heat sink, which is still not the hot side, but it's closer to the hot side than the outlet temperature, and that was actually 5 degrees hotter, so that was around 35 degrees instead of 30 degrees. So then I started to think, what can happen if I could directly measure the hot side temperature? Maybe the hot side is even hotter or even warmer than the cold side. So one thing is that maybe the thermal contact between the hot side and the CPU cooler was not good enough. I always clean off the paste and always put on new paste, but maybe the layer was too thick, too thin, whatever, I don't know. So I will test it again with that, but I don't want to dispose this video because still we can learn from this. This is like how to troubleshoot your measurements, because you see that your measurements are far off from your calculations, and then you have to think what is wrong and how can you solve it. So this is what we are doing now. This is not, yeah, it's a failure, but it's a failure that we can learn from, and basically no one got hurt or something. No damage was made to anything or anyone. It's just time. but that's totally fine, because it's this is something that we can learn from. So I noticed that maybe we are much more warmer with the hot side. So what I will do, I will take a closer look at this chart, and I will try to see how my voltages are, because here I should be somewhere here, let's say in between this area, right? Because we started at let's say T initial, that was 33 degrees, right? So if I started there, let's say that's somewhere here, and I was at 5 amperes, then we are at 12 volts, right? That's like, now it's lower. So then I should have read 12 volts if my temperature difference was something like this. So now let's see that. What could have happened if I am at 23 degrees? So let's go back to 23 degrees here, go up and go left. This is 42, oh, the magic number. Okay, this is exciting. But so here you can see that this is 42 watts. So this is a bit closer, actually it's a bit above the expected value. But now you see that the cooling power is much higher than here, 7 times higher. So the take-home message of this thing is that be very, very cautious with your temperatures and always read the charts, because these charts are basically just lines, but they tell so much to you that you cannot neglect them. So what you have to do here is always check that, okay, what is the DT that you are aiming for? And then what should be the voltage at a certain current settings. And if something is off, then you can go to the other performance chart, which is the DT versus QC, and see that, okay, then your DT is suggested to be 70, and then what was your QC then? and you can see that your numbers are off. But if I go backwards, I would needed something like this, so let's say 15 or 14 watts, or that was my calculation. So then still, if I go here, and that's like 58 dt equals 58 degrees Celsius. So then if I go here, 58, I mean this is already a very large number, so my hot side is still very large, but this is not it's still quite close, if you see that. So maybe this is even, I mean the difference is 3 between these, so halfway this is like 13, and then this is a little bit above 13.5. So I can imagine that I got the 14 watts. So the 14 watts is there, and yeah, this is something that if we are in this area, that works. But then that suggests that hey, something is off, and then this is off. The DT is too high, and that means that something is wrong with the cooling of the hot side. So what I will do with the next video, I reassemble this system. Maybe I go back to water cooling, because why not? And then I do this experiment again and see what are the numbers after doing it again, because I just cannot accept that I get these very funky numbers. So I would expect much better agreement, because if you remember, or if you haven't remember, because if you don't remember because you haven't checked the video, please check the previous video, where I got very nice agreement between the two numbers. And actually I can imagine that thing that it worked well there, because I was feeding so low current as compared to this current, that that could have actually worked. But since now I have the temperature curves, then I can see that something is wrong. So yeah. So what I want to do now is just conclude this video. So you could see that we can work with this thing and we can analyze all these things, but we have to be very, very careful about it. So I hope that this was useful to you, and you learned something, because I think I showed a lot of things that can be maybe useful. So then see you in the next video.